All right, let's get this started. So this is the Physical Geography 2 midterm review. So we're going to start off by me giving a few notes here. If you have any questions, please put them in the chat. There is someone else who is manning a computer who will be giving me the questions should you ask them. Additionally, if you have any questions for your instructor, because I realize that not everybody has me for their instructor for Phys 2, be sure to email them, especially if you have any questions about like attending the midterm. Those of you who are in my classes, you will come in during your normal class hours. Be sure to bring a computer or a something with which you can take the midterm on. Okay, and you come in and then you will take it in class. All right. Okay, so let's get started. So I'm going to talk very briefly about Labs 1 and 2. Labs 1 and 2 are very, I guess book heavy is the good word. Be sure to reread Labs 1 and 2. These two are very tightly related. The first is Map Essentials. Map Essentials, and the things you really need to focus on are your map distortion. Remember, distortions in area and shape and size, and in direction. Additionally, be sure to understand the difference between true north and magnetic north. So true north is pointed towards Polaris, right, where our North Pole is, and be sure that if you are asked a question about that, and I believe you should be sure that you put that it is pointed towards Polaris, where the magnetic pole follows the magnetic field of the Earth. All right, so that's going to be Lab 1. Lab 2 is topographic maps, and you will be given a topographic map in class. You will be given one, and you will be using probably the Jacksonville Quadrangle. That is one where if you have questions about the Jacksonville Quadrangle, we can discuss that in class before we start. But this is also why we are still doing, at least for mine, we're still doing our labs in person when we're doing the midterms. So, but the important thing to note from Lab 2 is how to read latitude and longitude. So be sure that when you are looking at the Jacksonville Quadrangle, remember that it was what was called a 7.5 minute series. Okay, so it meant that it was 7.5 minutes from top to bottom, right? But also 7.5 minutes from side to side. And yes, Cassidy, that one. Hello, by the way. Yes, the one from the 50s, the sad one that I don't really care for. Yes, that one. Be sure that you understand how to read Latin long. Again, for those of you who just joined, I am only be giving a brief review of Lab 1 and 2 here before we get into Lab 3, 4, and 5, which are much more hefty. So Lab 2, be sure that you understand how to read Latin long. Go back and reread these chapters. They are very straightforward and very direct. So, all right. So let's move along and let's get to Lab 3. Let's get to Lab 3. Lab 3. Lab 3, igneous rocks. So we're talking about igneous rocks for Lab 3. So let's review here for Lab 3. Bless you. We talk about the definition of a rock. The definition of a rock. And this will be a test question. And a rock is basically an agglomeration, if you will, of minerals. So basically, or the word aggregate, I like that one better, an aggregate of minerals, which is a collection of minerals. Okay. So a collection, let me just write this down, rock is collection of minerals. Okay. Sorry for my handwriting. It is what it is. All right. So a collection of minerals, an aggregate of minerals, right? That is the, I believe, the book definition. Okay. But these have different, a distinct way to classify them. So let's see, let's find a black marker so it's easier to show up. I'm not sure if that's showing up very well on the screen. So they are inorganic. They're inorganic. Okay. They have a definite composition. A definite composition, which means the molecules that make these up. You can typically find those throughout the rock. They have a composition, and then they have a crystalline structure that is defined. They have a defined crystalline structure. Okay. And these are three things that make up a rock, because we are starting the next 3 labs. We'll be talking about rock in its various states and forms. So, at 3. So when we talk about igneous, rocks. Igneous, right? Talking about rocks that are fired, right? That are formed from magma and lava. Magma and lava. We're going to come back to these here when we start talking about Lab 5. But remember, magma is molten material that exists within the earth, right? It has not been extruded. It is intrusive. Intrusive, right? Where lava is extrusive, and that is molten material that exists on the surface, okay? It exists on the surface of our planet. And this is typically talking about molten material. Igneous rocks are molten material that have solidified, okay? Solidified. So, this molten rock, basically molten rock that has solidified. So, a lot of molten rock beneath the surface, and we're going to come back to this again. This is so closely tied to Lab 5, and we are going to come back to this. But there are a lot of gases within some of these rocks, okay? And the way that some of those gases interact with the rock also helps form some of them. And we are going to talk about how this works. So if you were in my class, those of you watching are from my class, you will recognize what I'm about to draw. So we will have a chart, right? So we're going to have, this is going to be making a classification chart, okay? Because there are 2 ways you classify igneous rocks. 2 ways you classify igneous rocks, and that is texture and composition. So texture refers to really crystal size or the feel of the rock, right? The feel of the rock, right? So we're going to talk about texture. So we have a few classifications of that. Right? So we have texture. And then we have composition. Composition. All right. So, let's talk first about texture. Let's talk first about texture. There are 5 textures with which we are going to concern ourselves with. 5 textures, and we fill this out with a different color. So, texture, let's do, I like orange. Orange shows up. So, the first texture that we are going to talk about is phaneritic. Phaneritic. Is phaneritic. So, phaneritic rocks have large crystals. Large crystals, right? So, phaneritic, large crystals. And they have large crystals because the elements have had time to come together and almost congeal in larger, in what is like larger agglomerations or collections, right? And this is typically done because when we're talking about texture, we're talking about where something cools. Okay, this is also an important part to note, is that it cools intrusively. It cools intrusively inside the earth, right? And therefore, giving the rock, you can look at the rock and you can see like individual parts of it, okay, like the larger crystals, right? And then, inversely, we have something called aphanitic. Aphanitic. And aphanitic rocks, pardon me, aphanitic rocks cool extrusively and have very small crystals because they cool very rapidly. The individual molecules, the elements do not have a chance to come together and congeal. Almost, that's a, I'm kind of taking a liberty using that word here, but they don't have a chance to come together in such large quantities. The crystals there take less time to cool, right? And they cool quickly because on the surface of our planet is much cooler than the inside, which tends to be a lot of heat and pressure. So, phaneritic, big crystals cooled inside the Earth. Aphanitic, small crystals cooled outside the Earth. But you can have both. Yeah, porque no los dos, right? You can have both. It's porphyritic. Porphyritic. So let's say you are a phaneritic rock. That is like, hey friends, let's come together and make this collection of molecules that is a certain type of rock, right? And so they come together, they do that, and then the lava that you are currently swimming in, or the magma, is extruded, and you are rudely ejected back onto the surface of the Earth. And the molten material around you cools much more quickly than it was cooling inside the Earth, right? So you generally have two different types of crystal sizes in one, right? And this is called porphyritic. It is porphyritic. I'm going to lay these out, and then we're going to come back to, we're actually going to fill this chart in, and I'll tell you some of the names of some of those and how we can identify them. But it is crystals that have cooled inside the Earth, surrounded by crystals that have cooled outside the Earth, right? Okay. Next, we have glassy. Glassy. So, when something is glassy, this means that the crystals have fused together, right? That they have been cooled instantaneously. Okay? And this typically happens when molten material makes contact with water. With water, because it cools it like that. It takes no time. And it fuses the crystals together and gives it a very glassy texture. Okay? So you won't really be able to see the individual crystals like you can, especially with phaneritic or a little bit with aphanitic. It will generally be, yes, dragon glass, perfect. It will generally be very glassy, very shiny, also very sharp. Yeah, if you watch Game of Thrones, yeah, dragon glass. And the last one, pyroclastic. Pyroclastic, fiery chunks. Pyroclastic literally means fiery chunks. So it is molten material that is in one form or another cooled in like a chunk. And I'm going to fill this out and talk about what each one of these does here in a little bit. So let's go to our other axis. Hold on. I wrote the title where everything goes. Up there. Right. Let's talk about composition. 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 And we have three types of composition we have to talk about. And this, when we talk about composition, we're talking about the elemental makeup, right? So let's just jump right in. We have felsic. So felsic. And when we talk about composition, we're really giving it a very general, painting with a very broad brush here. So we're talking about the balance between heavier ferrous rocks, right? Lots of iron content, and lighter silicate rocks. Okay, we're going to come back to those. You're going to hear some of these things recur as we go through some of the labs. So felsic materials are high in silicates, right, and low in ferrous materials. This generally means that it will be lighter in color. Okay, you will generally be lighter in color and also lighter in weight. Typically lighter in weight. All right. Inversely, and I'm going to kind of like jump over here a little bit. You'll have mafic. Mafic is the opposite of felsic, so it is generally very dark, right? Very dark in color because it is high in ferrous content and low in silicate content, and therefore it is dark and also heavy. Very dark and heavy. Okay? Last one. Kind of left this one for last because boring, you know. Intermediate. Intermediate rocks generally fall in between, right? They generally have around between 40 and 60% of each one, and therefore have a grayish color. So you will see this in rocks that come from South American volcanoes. Generally tend to be intermediate. But let's start filling this out. Start filling this chart out. Let's use, what color should I use? Let's use blue. All right. So let's start talking about some rocks, right? So here, let's use a different color for the next one I'm about to talk about. There's a bonus question on the test for those of you who are my students. It's going to be, what's my favorite rock? So it's going to be the first one we're going to, the second one we're going to talk about. And we're going to talk about it first because I like it. It's going to be called rhyolite. And rhyolite is a felsic aphanitic rock. And this means that it is light in color and has very small crystals. Okay? Light in color, very small crystals. I'm going to keep that a different color because I like that one. It's going to be special. Okay. So what if something is felsic and phaneritic, right? What if something is lighter in color but cooled inside the earth? Well, that gives us granite. This might be something that you have seen. You might even have this in your house if you have granite countertops, right? So if you have a rock that is cooled inside the earth but is intermediate, well, we also make countertops out of this. Also, if you play Minecraft, this is in here. Diorite. Okay. And this one has a very salt and pepper texture to it. You'll see that it will have light crystals and dark crystals in equal measure. Okay. That you might be like, wait, but doesn't that mean that it's also? We'll get there. All right. What if something is phaneritic and mafic? That's called gabbro. All right. So these are all rocks that have cooled inside the earth, so they therefore have larger crystals, right? But are of different elemental makeups, right? So high in silicates, low in iron, high in iron, low in silicates, and generally strike a balance between the two. Okay. So let's talk about aphanitic rocks. We've already talked about rhyolite, right? I'm going to throw this hint out here again. Mr. King's favorite rock, rhyolite. Okay. Okay. So what if we have a rock that is aphanitic and intermediate? Well, that would be a boring rock. I mean, that's andesite. So, andesite, right? And take note that I talked about how this typically occurs in areas of South America, and take note of the word Andes, right? So the Andes mountain range in Chile, okay? you're in my class, you know that I like to break words down and we kind of talk about what they mean and it can help you figure out what's what, right? Okay. What if you have a rock that's aphanitic and mafic? Aphanitic and mafic. This is also what I like to parade around. This is basalt. You also find this around the Hawaiian Islands. Some other areas, okay. So what about something that's porphyritic? Well, okay. Porphyritic is more of a class than it is an individual rock, right? So you're basically classifying a rock. So if you have something that's porphyritic, you will just say that it is a porphyry, but then I'm going to leave a dash there because you might have, hear me out, I know this might be complicated to some, porphyritic rhyolite, porphyritic andesite, right? You might have individual crystals of different sizes within each one of these, right? So it's more of a prefix to denote that the rock that you're looking at has larger crystals entrapped within it, okay? Now, glassy. Glassy, this is one. So we talked about dragon glass already. This is obsidian. Obsidian. It's obsidian. So to review again, remember, these are rocks that have met with water and fused together, right? Pyroclastic, fiery chunks. Well, there are two different ways, two different ones we're going to talk about here. So I'm going to draw one. And the first one that I'm going to talk about, and I'm going to put it more toward the felsic lighter side, even though it can be different things, is going to be pumice. And pumice forms when gases escape from lava, right? So we're talking about above the Earth's surface. When gases escape from lava, and it leaves a lot of the material behind. But I'm going to put an important word to how you know something is pyroclastic. They don't have vesicles. They don't have vesicles. All right. Which means that it has these porous holes in the rock. So pumice tends to be almost like a volcanic foam that solidifies, right? The scoria is our last one. Scoria is talking about a rock that typically might fly through the air, but it has holes that are in it, generally darker and heavier. Okay. All right. Any questions about Lab 3 before we get into Lab 4? I'm probably going to spend the most time on Lab 4 because it's the one that also, if you're in my classes, this Lab 4 will also be a review for you to also do your lab, as most of you, we had inclement weather that week and did get a chance to make it up. So, any questions about Lab 3? Any questions about Lab 3? Gonna give it like 30 seconds. I'm gonna stand back and I'll wipe it here in like maybe 10 seconds. No. Okay. All right. So Lab 4 is going to be up next. If you're following along in your lab manual, it will be on page 28. 28 in your lab manual. I think, is that right? Yeah, that's Lab 4. Okay. So, Lab 4. Let's switch to a nice, rich blue. Lab 4. Sedimentary rocks. Sedimentary rocks. Okay, so again, if you are in my classes, this will be your kind of mini lecture for this. So be sure to follow along in your book. So, sedimentary rocks. All right, when we talk about sedimentary rocks, we have to understand that we are talking about taking another rock and breaking it down, right? So I always talk about breaking down words, right? So sedimentary sediment, right? So when you think of sediment, you think of maybe going into a river and you put your feet into the riverbed and you're like, wow, there's a bunch of sediment at my feet. That's generally what that strange feeling is. You wiggle your toes through the dirt and mud there, right? So sedimentary rocks, and when we talk about that, we are talking about a process. Creating a sedimentary rock is done through a 4-step process. I believe it's 4. Yeah, it's 4. A 4-step process. And we're going to talk about that process. So, step 1. Let's see, what color do I want to put step 1 in? What color would weathering be? We're going to do orange. All right. So, weathering. Weathering. So, weathering is done in 2 different ways. 2 different ways. 1, chemical, and 2, mechanical. Mechanic, man, my handwriting's bad. Oh well, we're doing this together, team. So chemical and mechanical. So chemical weathering occurs through breaking a rock down to its baser elements, right? So basically breaking it down to the molecules, okay? That is what chemical weathering is. And generally that is done with water, okay? Water is one of the greatest drivers of erosion on our planet, if not the single greatest. Whereas opposed to that is mechanical. So when you mechanically weather something, you are just breaking off pieces of it bit by bit. The book talks about how you break it down into something called clasts, okay? And these clasts are pieces of rock, right? Are pieces of rock. So the clasts are actually really important. This is actually a big part of your midterm. It's something that I think we're going to spend a few minutes here doing. So there are 4 different sizes of clast, okay? 4 different sizes, okay? And what we're going to do is I'm going to list these clasts, okay? So if we have mechanical, we're talking about mechanical here, okay? We'll come back to chemical. We don't have as much to say here. We're talking a lot about mechanical right now, okay? So we have 4 different sizes of clasts. So we have gravels, sands, silts, and clays. Gravels, sands, silts, and clays. Okay. These are the 4 different sizes of clasts. Okay, so if you're following along in your book, we're on page 29. But something to note is that the larger the clast, the larger the size, the more energy it takes to move, okay? The more energy it would take. So imagine if you had, let's say like a rock the size of like a fist, okay? A rock the size of a fist. Well, if you were to go down to, let's say the creek by the Lodiga Trail down here, right? A rock the size of a fist is going to be very difficult to move with how slowly that that stream bed moves. The water moves through the stream bed, right? It'll be very difficult to move that. But if you take that same rock, which is also the size of a fist, and you toss it in the Mississippi River, it's a different story. Because they have different amounts of energy, right? The Mississippi River is a large moving body with a lot of energy. There's a lot of motion occurring there, whereas a small creek nearby will not have the same amount of energy, the same amount of oomph to move something. So the larger the object, the more energy required to move it. So let's talk about the sizes of these, right? Gravels are typically 2 millimeters and up. Right? So that's generally like maybe the size of a pea, right? And higher. Okay? And we have sands, right? Sands, which are 2 millimeter to 0.05 millimeters. And if you've been to the beach or, I don't know, handled sand in any other way, you understand that it's still fairly small. It's rather coarse, right? It's coarse. It gets everywhere. I hate sand. Sorry. You will understand that size is still, you can still move an individual grain of sand in your hand, right? It's still rather coarse, but still kind of small. And you have silts. Silts. And this is 0.05 millimeters to, I think it's 0.002? Yeah, 0.002. Getting pretty small here. So the closest thing I can tell you that you can maybe have interacted with the size of silt is flour. If you've ever, or confectioner's sugar, that too. If you've interacted with either one of those, you know about the size of silt, even though it would be rather small. It would be really difficult to isolate a single grain of silt, right? But the last one we have is clay. It's really small, so 0.002 millimeters to a single molecule. So we're reaching a point here where clays are almost to the point that they have been chemically weathered, but are still mechanical, right? So are still objects that are still larger than a single molecule, okay? Because when it comes to breaking things down to their molecules, that is the purview of chemical weathering, okay? So this right here is something you need to know. You need to know this. I think there will be a matching portion on the test. If you can at least understand the sizes from greatest to smallest, so gravel, sand, silts, and clays. Gravel, sand, silt, and clay. Okay? You should be able to match up their sizes. Okay? So gravels are largest, sands and silts and clays are smallest. Okay? Any questions so far? Any questions so far? I see there are a few of you here. If you have any questions, please put them in the chat. So again, remember, the larger the piece, the more energy required to move it, right? All right. So once you've taken a rock and you've weathered it, right? Once you've taken a rock and you weather it, okay, you have to transport it, right? So the majority of the time, if you find a sedimentary rock, it also means that material was moved from somewhere else. And that's why our first step, I'm actually going to give weathering a number here. You know, A, B, look at that. I'm awesome. I did that. Okay. So, 2, transportation. Transportation. So transportation, I've kind of already told you about. So the larger the particle, the more energy required to move it. The larger the particle, or the larger the clast, if you will, clast, the more energy required to move it. Okay. Transportation is typically done by water. Although humans can also transport material. So if we're maybe digging something out to put a foundation for a house or something, we have to put the dirt somewhere. So this actually counts as transporting sediment. We're actually moving material from one place to another, right? That may eventually lithify into another rock. Okay. If you are doing it chemically, you will have, so if you have taken chemistry, you know that if you have material suspended in something, or you mix something with water, you create a solution. And it's called a solution load. Let me put up the difference here between, so mechanical and chemical. putting this in blue because it's typically done with water. Typically done with water. Okay. Any questions on this step? Any questions on this step so far? Any questions? Because we're about to go to the next step, okay? So, let's do purple for the next one. So once you have weathered it, right? Once you've weathered it and then transported it, it has to go somewhere, right? It has to go somewhere. So then we have deposition. Deposition. So no, this is not what happens before a trial. Deposition is what happens when you move this weathered material, you transport it, and then you deposit it somewhere, right? Then it finds its home to rest, if you will, okay? And deposition, again, you can tell a lot about the objects at an area where something has been deposited. You can tell a lot about the energy that it took to get it there. So if you find an area that has a lot of larger particles, you know that it took a lot of energy to get it there, right? It's not really about to put under here because we're just continuing to talk about. So you also have this, we're not going to get too far into this, but you'll also have what's called the marine model of deposition, where you will find that, let's say that this is, let's draw some pictures, friends. Let's say that this is the ground, right? And this is a riverbed, okay? This is a riverbed. You'll typically find that the closer to shore that you are, I'm going to use different colors here. You'll have larger particles the closest to shore you are. So you'll have your gravels, so G, right? And then you'll have your sands, right? And then your silts. And then your clay. My awesome pictures, right? So typically the closer you are to a shoreline or a riverbed, the larger the particles will be, okay? And as you go further in, you will find that the particle sizes will decrease and they will deposit like this, okay? They will deposit like this. Any questions? Any questions? We're about to go on to the last step. Last step. All right. The last step of this, so we've weathered it, right? Either chemically or mechanically. So if we've mechanically weathered it, it's been moved with a certain amount of energy from water. Or if we've chemically weathered it, it has gone into a solution and carried somewhere, right? And then it was deposited. Okay. Then it was deposited somewhere depending on the amount of energy required to move it. Okay. And then we have lithification. Lithification. So for lithification. It's like 4 eyes in that. Maybe. I don't know. Okay, yeah, there's 4. Okay. So, note, rock. Rock, right? Rockification. That's what this is. This is turning it into a rock, right? It's turning it into a rock. So once you have moved something, you turn it into a rock, right? And there are 3 ways to do this. 3 ways. 2 of them pertaining to mechanical weathering and 1 to chemical. So let's talk about the first 2 for mechanical. You have compaction, right? And cementation. So when you compact something, right? That means that you're taking something and you're pressing down on it, right? So it's constantly pressing down. So when you have something that is compacted, it means that weight has been applied. Weight has been applied. Okay? And generally, you will be able to tell something that has been compacted. You'll note that sometimes it will have lines to it, right? It may have what are called foliations, okay? And also, it tends to like catch on other rocks. So you might have like a good mixture of other rocks within your clast, your conglomerate, if you will, which is a collection of multiple particle sizes. But if you cement something, it means that you've brought a particle into a bunch of other smaller particles, right? And this is kind of like, this kind of mirrors what happens with porphyritic rocks, right? You have larger particles that are cemented within smaller particles. And that is what happens with cementation. They tend to get locked in, right? So you can compact it, right? You can compact it, or you can do cementation, which is basically gluing rocks together. That's kind of what cementation is, okay? And these are both mechanical, right? And the last one is precipitation. Precipitation. And this is chemical. And this is that solution coming to rest. That is that solution that is precipitated onto an ocean bed or a stream bed, right? So the particles no longer move, they find a home, and they start to precipitate, and over time they will form a rock, okay? All right, any questions? Any questions? This is the Lab 4 lecture. I like condensed this. This is basically Lab 4 right here in its entirety. If I have written it down on the board here, please know it going into the midterm. This is very important. I will also be pushing this in another announcement once this is over, those of you who are in my class, because this is something that you'll have your lab done by your midterm, which most of you don't see me until Thursday anyway, so plenty of time. Okay, any questions about Lab 4? Anything at all? Because we're about to go to the last one. Should be right on time to be like an hour here. Any questions, class? How you doing, class? Don't say anything. No. Or, all right.
Casey's Stencil would like to know, what are you eating?
Trail mix. Oh, hey, Casey. Glad you're here. Yeah, I'm eating trail mix. Really good. Yeah. Okay. All right, team. One last lab. What do you want to talk about? Let's use. We're going to do orange, black, and red for this. Lab 5. Lab 5. Volcanoes. Those of you who got to see me teach this, you know I love this. This is the good shit. This is the stuff that we're really gonna. This is easy. Lab 5 is also, I will say, probably one of the easier ones because everything is laid out in your book. But we're going to talk about it. So, when we talk about volcanoes, there are a few baselines we have to set. Okay? So, lava, right? A molten material that exists above ground, right? Above ground. Okay? Magma, molten material below ground. Molten material below ground. So lava and magma. So if you are on the Hawaiian Islands somewhere, which would be super cool, and you look out and you see that there is molten material above ground, you're looking at lava, right? If you are seeing lava, then I'm going to tell you that you are standing above magma, right? That you cannot see. So volcanoes erupt because of something, because of one word. One word causes volcanoes to erupt. Pressure. Pressure. Pressure causes volcanoes to erupt. Pressure of what? Well, this is pressure of gases that are trying to escape, right? That are trapped within magma, right? And a lot of volcanic eruptions are just water vapor and ash. Just water vapor and ash. It contains very little CO2, very little other gases. It is mainly just water vapor, which is H2O, and just molten material, ash, right? So what will happen is if, let's say you took a soda bottle, this is what I think I've mentioned like ad nauseum. You take a soda bottle and shake it up, right? So you shake up that water bottle, and at the top you will see that there is like, you know, the foam, and that's basically the gases separating from the liquid, right? And if you open that up, it erupts, right? It goes everywhere. The concept here is basically the same. It is contents under pressure, right? So if you have enough eruptions or enough molten material being pulled out of the earth, you can start to form volcanoes. And we're going to talk about two ways with which you can form volcanoes. Okay? And the first one is called subduction. Subduction. So let's put this one, subduction. Subduction, okay? And subduction is when you have plates that meet and one subducts beneath another. So I'm gonna visualize this. So typically this happens between boundaries between continental and oceanic plates. And oceanic plates, remember our tectonic plates do move over time. The tectonic plate, this is the oceanic, right? The plate will move towards the continental plate, right? Which is right here. So this is our continental plate, right? And something to note, and let's harken back to lab 3 here. We know that continental plates are typically high in silicates, right? And silicate material is very light, okay? Where oceanic plates tend to be very high in mafic material, right? So this plate will dive down beneath the continental plate. It is heavier, and what will happen is the continental plate will kind of surf on top, right? And it will plunge down into the earth, okay? And this is kind of the eternal cycle of Earth's tectonic plates, is they keep moving, and they reach a point where they will return back into the earth as new material is formed on the other side, right? It's kind of a millions of years long circular motion that continues. So that plate will subduct beneath, but as it does so, the further you get down into the earth, the more heat and pressure there is, right? The more heat and pressure, so it will melt. It'll melt, right? It'll melt. Well, what will happen there is because Earth spins, okay, we have a spin. Gravity has a push and a pull on Earth. Okay, what will happen here is that molten material will be lighter than everything else around it, so it will be pulled outward, right? So it will continue to rise, and if there is another plate above it, it will cut right through it. And generally what we get here is a volcano. Right? Is volcano. Fantastic artwork. Okay. Let's give a little bit of ocean water right here. If you were in my class on Thursday, I drew the shark, right? The shark was awesome. Okay. So these are characterized by two distinct things that happen there. One, you get a trench, right? So there's a trench that forms. Okay, so if we're familiar with the Mariana Trench, which is the deepest point on the surface of our planet, okay, the deepest point on the surface of our planet is basically an area where a plate is subducting beneath another. And there's so much life down there because there's so much heat, right? Geothermal heat is released, that's what I was looking for. In this area, you get a trench, but also you will typically get, in the same area, strong earthquakes. Where the plates meet, you will typically get strong earthquakes because it is that grinding together of two large objects, two massive objects will cause earthquakes. Okay? All right. So the next one is hotspots. Hotspots. Okay. So I'm going to do it this way. It's really hard to visualize this on camera, so we're going to do it like this. So imagine this is a plate, right? Imagine this is a plate. And below that plate is just a big old pool of magma, right? That's trying to make its way up, right? So what it will do is that magma will break through. That fountain of magma will break through. And typically what will happen here is it will start to create a volcano, which then turns into, if you are underwater where this occurs, right, an island, okay? But remember, I said when we were talking about this, when we're talking about subduction, that plates move, right? Plates move. So let's draw this plate again a few million years later as the plate has moved. Okay, well, you're going to have your original volcano that was formed, but it will no longer be above that vent of magma, right? So what will happen again is it will rise, okay? And it will create another island, right? So let's make this a little bit smaller, okay? It's a little bit smaller. So it is cutting through, right? Creating a hot spot that cuts through. And then, maybe a few million years later, you come back and you look at it again, and you see that you have the first island, right? And then the second island. But because the plate has moved, you will get another island. Okay? The plate has moved. The important thing to note here is that the hot spot, right? The hot spot where the magma is does not move. The plate moves over it. And as this happens, I'm going to try and draw a very familiar landform here. You'll get islands that form, okay? Like the Hawaiian Island chain. Like the Hawaiian Island chain, which is a direct result of a hotspot. Right? A direct result of a hotspot. So remember, the hotspot never moves. The hotspot does not move. The plate moves over it, and new landforms are built, right, as that occurs. Okay. Any questions? Any questions? There are two more parts to this, but I want to make sure that we have this down. Let me stand back, so if you want to, like, I don't know, anybody watching it in the future, I'm going to stop and take a look at it. Any questions about this? All right. So these are the two ways to form a volcano that you have to know for your midterm. So we have subduction, right? One plate subducts beneath another, okay? And hotspots, where a plate will move over a hot spot where magma is being extruded. Okay? Okay. Now for part 2 of 3. Part 2 of 3, we're almost done. We're almost done. I have like a little bit to explain, and then we're going to draw some more pictures, and then we're done. And then we're going to be done. Okay. So the next thing that you have to know, if you are in your lab manual or on page 39, is the 3 different types of lava. 3 different types of lava. Okay? So the first is, let me just pick different colors here to put these in. The first is It's called okay? And it says it's primarily basaltic, right? But it is highly viscous, high viscosity, okay? High in viscosity, lower in temperature. So when we talk about viscosity, we're talking about the thickness of the lava, the consistency, right? So when we're talking about something that's high in viscosity, it's almost like a cough syrup or glue or molasses or syrup, like something that just that flows very slowly, okay? So it tends to be high in viscosity and lower in temperature, as opposed to the second one, Ahoy, is the exact opposite. It's low in viscosity, right? Low viscosity and high in temp. This would have the consistency of like water, right? So water has low viscosity, right? And this lava would be high in temperature, okay? And last is pillow lava. Seems a lot of place, doesn't it? Pillow lava. And this is underwater. This is underwater, and this tends to form shells. To give you an idea what this looks like, this would be, so if here's the ocean surface, okay? And the material is coming up through, or maybe it is somewhere else, it will be this shell-like object, and then inside, do some of that back, right? It'll probably take some time to cool, but it will get there. Okay? Any questions? Any questions about the types of lava? Because we're about to get into the very last part of this review, because we're going to talk about actual volcanoes. Yee. See you on Thursday, Cassidy. All right. Almost done. Almost done. So now that we have this, all right. So now let's talk about the types of volcanoes. Let's talk about types of volcanoes, and I'm going to draw some pictures here. So, the types of volcanoes, we have 3 that we need to talk about. Okay? So the first is called a cinder cone. Cinder cone. So if I asked you to draw a volcano, most likely you would draw something like a cinder cone. You would just give a typical high-sloped mountain, right? With a little part at the top. And they typically are called that because they have a bowl right at the top. And that bowl is generally full of volcanic cinders, okay? And this is also characterized by a single distinct vent, or a single magmatic vent that runs up to the top, right? This is the central vent, okay, where most of the magma comes out of, okay? And these are typically only 1,000 to 1,500 feet tall. 1,000 to 1,500 feet tall. Okay. So it's a cinder cone. Okay. The second we're going to talk about is a composite volcano. Composite. And these are also called stratovolcanoes. Stratovolcanoes. And these are typically large volcanoes, right? Very large volcanoes. Okay, I'm making this one much larger than the other one. And these typically have a central vent, right? Central vent. But they also have features called fissures and dikes, okay? That tend to branch out to the side, okay? Tend to have fissures and dikes that branch out to the side. So a central vent, right? And then areas where lava can also extrude. Remember the word extrude when it exits the earth, right? And these are generally pretty large. The most violent volcanic eruptions that we talk about are generally from composite volcanoes because a lot of the time the pressure will not just build up at the top, it will build up along the side. So you will have, like Mount St. Helens, you will have a volcano that explodes sideways. Basically explodes outward as well as upward. These are very dangerous, very powerful, okay? And usually very large. We're talking about Mount St. Helens. The volcano in Tonga, Pompeii was also a composite volcano, right? All right. And the very last are called shield volcanoes. Shield volcanoes. And this typically happens when you have, I'm going to draw the Earth's surface here, when you have magma that exits the Earth, but then it spreads, right? It spreads out and keeps spreading out, and then it cools. So it turns into a large, very wide volcano, right? That can get very large, very wide, and very tall. For reference, the largest geologic object in our solar system is on Mars. It's called Olympus Mons, and it is a shield volcano that is, I think, about, 60-something miles wide? It's really wide. I don't know. It's tall. Additionally, the largest landform on planet Earth, I know we talked about Mount Everest being the highest. It is not. It's the highest above sea level. As it turns out, Mauna Kea, which is one of the Hawaiian Islands, is the largest landform on Earth, because if you were to measure it from the under the ocean, right? So at the seabed to where it starts to where it ends, it would be, I think, almost 20,000 feet taller than Mount Everest. So this typically occurs when lava is extruded, is extruded, turns into lava, and then it cools, and then it just keeps happening over and over, spreading out to create this very large, wide, round, platformed area. So, all right, any questions about this? Any questions about this? At all? Any questions? Because we are about done. We're about done. All right. Well, team, your midterms for me. If you're in my Thursday class, please show up on Thursday night. If you are in my Friday class, I'll see you Friday morning. Also, Lab 4 was included in this. What I want you to do for Lab 4 is give me an overview of each step of the process, each step of the sedimentary rock formation process, right? And a lot of that will just be what I had listed up here, okay? What I had listed up here. I'm going to post this again in an announcement. I'm probably going to provide timestamps, be like, please start here, and watched it here, or just watch the whole thing. It would be to your benefit. So do I have any questions? Any questions at all? Oh, if you have any late labs, please get them to me by your class period. Because after you take your midterm, the grades are out of my hands. So, any questions? I'll give it like another minute before I end the stream. Right. Okay. Well, thank you for coming to the midterm review. Good luck. I will see you in class. And thank you for attending. All right. Bye.